Hi, my name is Misha Piermike, and I'm the sales manager here at Quantic Evans. Today's webinar is Unlock the Power of Avionics, the Capacitor's Critical Role. I've helped hundreds of engineers specify capacitors for their unique avionics applications, and today I'll be sharing some of the best key practices to employ. This webinar will guide you through the critical criteria for choosing the best capacitor to meet the unique demands of avionics applications. So, for our agenda, we'll start with a brief introduction to aviation and avionics. We'll then review the critical role capacitors play in avionics designs, design criteria for capacitor selection, types of capacitors you'll typically see in avionics applications. And finally, we will present two design scenarios that you might be presented with in your work. So let's get into it. Now, when and where did this all start? On December 17th, 1903, brothers Orville and Wilbur Wright made the first successful sustained flight of an engine-powered aircraft. By the 1950s, global commercial passenger flights became commonplace. Today, we rely heavily on aviation for nearly every aspect of our lives, from global trade and commerce to travel and tourism. Worldwide militaries utilize avionics heavily as a key and central part of their defense strategies. Now, did you know that in 2024, there were approximately 39 million commercial flights worldwide, and global passenger traffic exceeded 4.5 billion travelers? Now, this is actually expected to double by 2037, reaching 8.2 billion passengers per year. During this time, aviation safety has improved dramatically, with the odds of fatal accidents now at about 1 in 11 million flights. The commercial drone market grew to over 43 billion in 2024, highlighting the expanding role of aviation technology beyond traditional flight. These statistics illustrate the dynamic nature of the aviation industry and its ongoing advancements. The world of aviation continues to transform our everyday lives, and avionics has become central to that transformation. So, what is avionics? Well, simply put, avionics is defined as electronic equipment fitted in an aircraft. Modern aircrafts contain a suite of avionics equipment, including sophisticated navigation, communication, power, autopilot, and sensing systems. Military aircrafts typically contain even more of these avionics systems, such as radar, target designators, IFF, or identify friend or foe systems, and weapon systems that help increase the effectiveness of the warfighter while improving their safety. Drones and missiles also share many of the same requirements. While avionics systems are found throughout an aircraft, the cockpit is where a majority of these integrated avionics systems are housed. These systems are crucial for flight operation, navigation, communication, and overall aircraft management. Key systems located in the cockpit include the flight management system, which is a computer that manages flight planning, navigation, performance calculations, and data logging. Now, this actually interacts heavily with other systems. Other systems do include autopilot, traffic collision avoidance systems, ground proximity warning systems, radio communication, navigation systems, flight data recorders, weather radar, and much more. Now, let's examine the critical role capacitors play. Capacitors provide essential functions within avionics systems, such as energy storage, voltage regulation, and noise suppression. They also ensure the stability and reliability of power supply circuits, allowing critical systems to maintain operation during brief power interruption events. Additionally, capacitors help filter out electromagnetic interference, otherwise known as EMI, and high-frequency noise, thereby protecting sensitive avionics components and enhancing overall system performance. Specifically, Capacitors provide power management, signal integrity and noise reduction, and safety and protection. Now, let's take a closer look at each of these functions. Capacitors help maintain stable power supply voltage by decoupling and filtering out high-frequency noise. This is crucial for sensitive avionics equipment. Capacitors store energy to maintain critical electrical systems continue to have power during brief power interruption events, typically providing power holdup times of at least 50 milliseconds, as defined by standards such as MIL Standard 704 and DO 160. They provide energy when needed, which is important for systems that require uninterrupted power. Capacitors also assist in voltage regulation, helping to maintain consistent power levels across avionics systems. To optimize signal integrity and noise reduction, capacitors are used for input-output matching and coupling in RF circuits, maximizing power transfer and minimizing signal reflections. Capacitors act as DC blocking components, allowing only AC signals to pass between circuit stages. This is essential for proper signal processing in avionics. They suppress electromagnetic interference, which is critical in the electrically noisy environments of an aircraft. Capacitors are used as snubbers to suppress harmful voltage transient spikes, protecting sensitive components that can be damaged or experience reduced operating life if exposed to an excessive number of these spikes. They serve as safety components in high voltage systems, helping to mitigate the hazards that can be seen with dealing with high energy applications. By fulfilling these various functions, capacitors play a pivotal role in ensuring the reliable, efficient, and safe operation of modern avionics systems. When selecting the best capacitor for a unique avionics application, you will need to consider key critical design criteria, which include high altitude, shock and vibration, failure modes, derating, temperature, energy and power density, and assembling the capacitor. So let's take a closer look at the specifics of each of these criteria. Now, we must be mindful of how the capacitor operates and behaves at high altitudes. Since the pressure is significantly lower at high altitudes, non-hermetic capacitors can leak electrolyte, introducing a variety of reliability and safety issues. When designing for high altitudes, hermetic capacitors are a common requirement. Now, although it's commonly thought of as meaning airtight, hermetic really means that gases and moisture cannot penetrate the capacitor, nor can they escape. Designers should verify a capacitor's altitude rating. A common one is MIL Standard 202, Method 105, Condition D, which specifies a 100,000-foot altitude test. If the capacitor meets this test requirement, it is considered well-suited for avionics applications. Now, avionics systems are exposed to vibration, particularly in the case of rotary wing aircrafts such as helicopters. Today's modern airborne weapons, such as missiles, contain their own avionics subsystems, which must be able to withstand the aggressive shock conditions. MIL Standard 202 defines a wide variety of shock and vibration conditions that an electronic component must meet. It's important to ask the capacitor supplier which MIL standards that particular capacitor adheres to. It's always a good idea to plan for the unknown. Despite a designer's best efforts, failure happens. While capacitor failure happens, understanding their failure mode or the way a particular capacitor fails is critical for maintaining system integrity and safety. For example, while solid tantalum capacitors are widely used, when they fail, they can fail catastrophically and open, and even sometimes by catching fire. Other capacitors can swell either as a failure mode or even as they simply approach the end of their life. This can and will impact other components and subsystems around it and could render the entire vehicle useless. A designer must understand how the capacitor fails to account for this in their design. The lifespan of the mission typically dictates the needed lifespan of the capacitor. Typical D-rate criteria are defined in various mil standards. A 50 to 60% voltage D-rate is typical, but can vary depending on individual mission profiles. Primary factors that impact capacitor life includes the capacitor's duty cycle, operating temperature, and operating voltage. The lower the operating voltage and temperature, the longer the capacitor will last. Due to the aggressive reliability requirements demanded in avionics applications, designers must derate, choosing a capacitor with a much higher voltage and temperature range than seen in the application. An aircraft sitting on the runway on a hot summer day can reach very high temperatures. During operation at high altitudes, the temperature outside of an aircraft can dip down to -6 degrees C. Different capacitor technologies have different temperature ratings, so attention must be paid to the capacitor's operating temperature range during selection. Some also have significant performance variation as their ambient temperature changes. For example, some capacitors have much lower capacitance ratings at cold temperatures and can lose half or more of their nominal or room temperature capacitance at extremely low temperatures commonly seen in avionics applications. Accounting for the worst case scenario in low temperature environments is a key part of the capacitor selection process. Other capacitors, such as multi-layer polymer film capacitors or MLP capacitors made by Quantic Paxtron, have very stable performance across temperature. This is based on the unique materials and construction methods of these MLP designs. Now, the capacitor's energy density is the amount of energy stored in a capacitor per unit of volume. This is a key component as the higher the energy density is, the more volumetrically efficient the capacitor is. The capacitor's energy density is calculated by dividing the energy stored in the capacitor by its volume. We first start off by calculating the energy stored within the capacitor by using the equation we see here on the screen. E equals 1/2 CV squared, where E is the energy stored in the capacitor, C is the capacitance rating of the capacitor, and V is the voltage rating of the capacitor. Once we calculate the energy stored, we divide it by the unit of volume to obtain the capacitor's density. Different capacitor technologies have widely different energy densities, so it's an important attribute to understand when comparing capacitor options. Like energy density, power density is measured by calculating the energy delivered by the capacitor per unit of time. Since avionics applications are so volumetrically constrained, they can be very sensitive to power density. To calculate the power density, we start by calculating the power using the following equation. P equals E over T, where P equals the power delivered by the capacitor, E equals the energy stored within the capacitor, and T is the pulse width, or the length of time needed to deliver the specific amount of energy. Designers must confirm that the capacitor can handle the application's required power needs, which is usually done by checking the manufacturer's datasheet or contacting them directly. Once confirmed, the power being delivered by the capacitor is divided by its volume, thus giving us its power density. Power densities of various capacitor technologies vary significantly. For example, hybrid wet tantalum capacitors, like those manufactured by Quantic Evans, have the designation of being the most power dense in the world. They are often compared to aluminum electrolytic capacitors. Surface mount devices, or SMD capacitors, offer a low-cost, large capacitance to footprint ratio, while through-hole capacitors provide reliability under harsh environments due to the stronger mechanical bonding. Some designers prefer the use of SMD capacitors, but not all capacitor technologies are available in this format. Due to the vibration environment seen in avionics applications, ensuring that capacitors are assembled in a way that protects them from shock and vibration is vital. Check with the manufacturer for recommendations as to how to best install the capacitor for each unique application. Common types of capacitors most often selected for avionics applications include ceramic, film, tantalum, aluminum electrolytic, and hybrid with tantalum. Now, let's take a closer look at the advantages and limitations of each. Ceramic capacitors have a long legacy of use in avionics and typically are selected for their reliability, resistance to vibration and shock, and excellent high-frequency performance. Some notable advantages include high reliability and stability in harsh environments. Now, this makes them very well suited for extreme conditions typically encountered in aerospace. In addition, excellent high frequency response, a compact size and low profile, and this is especially true for multi-layer ceramic capacitors, otherwise known as MLCCs. And this helps reduce the overall size and weight of the avionics equipment. They are non-polarized in nature, allowing them to be used in both AC and DC circuits. They're also known for having relatively low ESR or equivalent series resistance and ESL equivalent series reductance. And they're offered in a very wide range of capacitance values from picofarads to microfarads. Now, some limitations do include that the capacitance value can actually decrease significantly as the applied voltage reaches the rated voltage. Now, this is especially true in smaller package sizes and higher dielectric constant materials. They are susceptible to mechanical stress, which can cause changes in capacitance or even cracking in extreme cases. Some capacitors, particularly class 2 dielectrics like X7R, exhibit significant capacitance change as the temperature changes. Also, ceramics have the potential for negative impacts as a result of piezoelectric effects, which can introduce unwanted noise in some circuits. And they are limited in maximum capacitance values compared to other capacitor technologies, and typically they're available in up to 100 microfarads. They are also sensitive to DC bias voltage, which can reduce the effective capacitance in power supply applications. And finally, they do risk thermal runaway in high voltage applications if they are not properly derated. Film capacitors are particularly valued in avionics for their reliability, electrical stability, and their ability to withstand harsh environmental conditions, making them suitable for many critical applications in aircraft electrical and electronic systems. They do come in a variety of form factors, including wound and stacked. Now, some advantages include they are highly electrically stable over life and temperature. Particularly MLP or multilayer polymer film capacitors are mechanically flexible and they are not susceptible to the cracking as seen as MLCCs. They are known for having low ESR and low ESL and are well suited for high frequencies. They're also non-polarized and they exhibit high insulation resistance, making them well suited for AC and DC applications. They are self-healing. That's the inherent nature of film capacitors. They are self-healing, and they do have a long shelf life and a long service life. They're known for being highly reliable with low failure rates, and they do have the ability to withstand high voltage spikes. So some limitations include the fact that they are physically larger when compared to ceramic or electrolytic capacitors for equivalent capacitance ratings. They are lighter than MLCCs, but they are physically larger. Generally, they do have lower capacitance values when you compare them to electrolytic capacitors. In addition, they are more expensive than some other capacitor types, and they are limited in their availability in the surface mount packages for space-constrained applications. Now, avionics designers select wet tantalum capacitors for their combination of high capacitance and reliability in the demanding environments typical of aerospace and avionics systems. Their highly desirable swap or space, weight, and power optimization advantages must balance with their cost. So some advantages include the fact that they have high capacitance values in really small sizes. They perform very well, excellent stability over life and over temperature. They're relatively low. They're actually very low in ESR, and they're known for their high reliability and long service life. They do have the ability to withstand high ripple currents, and they're often offered in hermetically sealed options. They do have a very wide operating temperature range, typically from -55 up to 125 degrees C. Now, some limitations include the fact that they are higher cost when you compare them with other capacitor types. They are polarized, which means they are generally limited to DC applications. They do have the potential for internal gas pressure buildup, which may cause them to swell. They are larger in size than some of the newer technologies available today, and they do have limited availability in surface mount configurations. And in some silver case capacitors, they do offer the potential for silver migration. Now, avionics designers select aluminum electrolytic capacitors for their combination of high capacitance and low cost, along with their ability to handle the demanding environments typical of aerospace and avionics systems. However, their limitations, particularly in terms of lifespan and temperature sensitivity, must be carefully considered in design and maintenance planning. Some advantages include high capacitance values and small package sizes. They're low cost compared to other capacitor options, and their high voltage ratings are available. They do have good self-healing properties, and they're known for having a wide range of capacitance and voltage values. Limitations do include the limited lifetime due to electrolyte evaporation. They are sensitive to high temperatures, and they are polarized. In addition, they're known for having a bit higher ESR compared to other capacitor types, and they're limited in performance at high frequencies. And finally, they do have the potential for the electrolyte to leak. They are limited in performance at high frequencies as well. Hybrid wet channeling capacitors, made by Quantic Evans, are known for being the most power dense in the world. They also provide a very energy-dense option for low to medium voltage applications. Advantages include a wide range of capacitance ratings from within the 10 to 125 volt range. They're hermetically sealed and very well suited for high altitude applications. They're exceptional at their ability to withstand high shock and vibration environments, and they do have a wide operating temperature range from -55 to 125 C, and some even go as high as 200 degrees C. These capacitors have a long history of success being used on a variety of commercial and military applications. Now, some limitations include the fact that they're not always volumetrically ideal for higher voltage applications. They do have their sweet spot. Unique hybrid technology does use expensive materials, making hybrid wet tantalum capacitors more expensive than other technologies. And similar to other types, they are filled with electrolyte, and the electrolyte may leak if the capacitor is not properly mounted to the circuit. Now, let's step into some design scenarios and see how some of these different capacitor technologies compare. Let's say an engineer is designing a next-gen airborne early warning system. This engineer needs a capacitance for high speed, low noise, analog to signal path within the radar's receiver. This signal path handles frequencies up to 1 gigahertz and requires minimal signal degradation. The capacitor must meet the following specifications seen on the screen that include a 100 nanofarads with a somewhat tight tolerance of plus or minus 5%, 50 volts, and so forth as seen on the screen. So let's say 4 different technologies are evaluated. Here's how they break down. Now, while offering high capacitance values, electrolytics typically suffer from high ESR and ECL at high frequencies, making them unsuitable for this application. Their relatively low temperature range and susceptibility to high shock and vibration also further disqualifies them. Now, ceramic capacitors offer a good balance of size and capacitance. However, depending on the dielectric material, class 1 or class 2, their temperature stability and high frequency performance might not meet the tight tolerances set by this design. Class 1 ceramics often offer better stability but lower capacitance values, while Class 2 capacitors have higher capacitance values but poorer temperature stability. Therefore, they might not be the best or most optimal solution for these stringent applications. Now, solid tantalum capacitors offer high capacitance in a small package. However, they do have limitations with high frequency applications and might not be ideal for this 1 gigahertz application. Also, their failure mechanisms are potentially catastrophic, something we need to minimize. Lastly, multi-layer polymer film capacitors, or MLPs, excel in high-frequency applications due to their significantly lower ESR and ESL compared to other types. Their inherent robustness makes them well-suited to withstand the shock, vibration, and extreme temperature ranges defined in mil standard 810. Furthermore, polymer film capacitors generally demonstrate high reliability and long life, aligning perfectly with our 10-year operational goal. The available capacitance range also easily accommodates our 100 nanofarad requirement. The smaller size is also attractive. Now, in this design scenario, we're designing a newer power system for a critical avionics component within a military aircraft, specifically a high-precision inertial navigation unit, or INU. This unit requires unwavering power stability and must maintain functionality even during brief power interruptions. Compliance with mil standard 704F for power holdup is mandatory. The INU requires a constant 28-volt DC power supply at a minimum of 1 amp for at least 100 milliseconds during a primary power interruption. The system must continue to operate within specification to prevent loss of navigation data and ensure mission continuity. We are concerned with both the power holdup time and the stability of the voltage supply during this interruption. Excessive ripple or voltage drop could lead to INU malfunction. So here are the specific requirements. Our voltage is 28 volts DC, and our holdup time is a minimum of 100 milliseconds at 1 amp, which essentially makes this mil standard 704F compliant. And the maximum voltage ripple during holdup will not exceed half a volt DC. This stringent requirement for the application, particularly the 100 millisecond power holdup and 1 amp with minimal voltage ripple, and the need for mil standard 704F and mil standard 810H compliance, and the demand for extremely high reliability, dictate a careful evaluation of various capacitor technologies. Now, with aluminum electrolytic capacitors, they do offer a cost-effective solution, but electrolytics do suffer from higher ESR, again making them unsuitable for the low ripple requirement. Their limited lifespan and temperature range don't really align with the long-term reliability and extreme operating conditions. Compliance with mil standard 704F specifications with this technology would really be unlikely. Now, ceramic capacitors do possess low ESR, but their energy density is too low to meet the 100 millisecond power holdup requirement time without a probability of a large and heavy capacitor bank. Now, similar to ceramic capacitors, film capacitors lack sufficient energy density for this application. Hybrid wet tantalum capacitors, on the other hand, excel in applications demanding high reliability, long life, low ESR, and stable voltage delivery. The low ESR is crucial for minimizing ripple during discharge, directly addressing the mil standard 704F requirements for voltage stability. Their superior performance over a wide temperature range aligns perfectly with the specified operational conditions. Their inherent robustness and design features aimed at preventing catastrophic failure meet the stringent reliability needs of a mission-critical system. So we conclude that the combination of high reliability, low ESR for voltage stability, adequate energy density to achieve the 100 millisecond holdup time at 1 amp, and compliance with relevant military standards make the hybrid wet tantalum capacitor the ideal solution for this INU power holdup application. This choice mitigates the risk associated with less reliable capacitor types and ensures consistent, stable power to the INU, even during brief power interruptions. Further steps would involve detailed simulations and testing to verify compliance with mil standard 704F and to optimize the capacitor bank design for size and weight while maintaining performance requirements. So, in the complex and critical field of avionics, the selection of capacitors demands a meticulous approach that balances performance, reliability, and cost. Best practices in this domain emphasize a holistic view of the entire system lifecycle, from initial design to long-term operation and maintenance. Choosing the right capacitor will help designers make avionics systems that are smaller, lighter, and more efficient. With so many capacitor options today, partnering with the right capacitor supplier will help ensure the best capacitor is being chosen for each unique application. And thank you. And now we'll move right along to our questions and answers.
Do commercial aircraft have to comply with MIL Standard 704?
Great question. So we here at Quantic Evans deal with MIL Standard 704 all the time. Our capacitors actually tend to be extremely popular for these applications. And we do get these requirements from both commercial customers and military customers. This is more of a military geared specification. However, a lot of commercial aircraft manufacturers, that MIL spec is so robust that it does oftentimes get adapted by a lot of commercial customers as well there too. So yes, we've seen it in both places, despite the fact that this is really a mil spec.
The next question, are wet style electrolyte filled capacitors suitable for avionics applications?
Ah, yes, we get this quite often. Now, there is a fear of designing these capacitors in avionics applications because if it's filled with an electrolyte, which is typically conductive and perhaps corrosive, there is a potential to leak. However, the likelihood of the capacitor leaking when installed and designed in properly is almost negligible. There's ways to secure the capacitor of the board such that you're not imparting stress on, perhaps sensitive terminations and things of that nature. So the short answer is yes, absolutely. Wet style electrolytic capacitors are perfectly suited for avionics applications. The one thing we just ask is work with the manufacturer. Get on a call with someone such as myself or a member of our, technical team, and we will give you the step-by-step instructions and guides as to how to properly secure that capacitor to your board, to essentially, make that scenario a non-issue. But yes, these capacitors are widely used today in a wide variety of avionics platforms.
So the next one is, how much can performance vary at low temperatures?
Oh, so depends on the technology. Some capacitors at extremely low temperatures, and we're talking -40 to -50 degrees C, they literally can lose up to half their capacitance when you compare their capacitance to that of room temperature. So when designing in a capacitor, you have to think of the worst case scenario. What are your capacitance needs at that worst case scenario? At room temperature, you might have more than enough capacitance, but as soon as you get at altitude where the temperature is much lower, with that capacitance potentially cutting it in as much as half or more, that's your baseline. Oftentimes, there's other areas of design to look at, but oftentimes, that's your baseline. Worst case scenario, and that's where you start. And how much capacitance do you need at that worst case scenario? But again, the short answer is it depends on the technology, but up to half of the capacitance can be lost at extremely low temperatures. Some technologies have about, for example, multi-layer polymer film capacitors. It's nowhere near half. The electrical performance at these low temperatures is far more stable. So and ask the manufacturer for if they have these graphs, this performance data, or the EIS data, such that you can make the best decision for your design.
Last question, what is the most often seen D-rate criteria?
60%. That's pretty typical. Some designers will shave that down to 50% if there's a good case. But 60% voltage derate, and of course, you derate by voltage, you also derate by temperature. And you can get an approximate doubling of life for every 10 degrees below the operating temperature that you're operating. So temperature and voltage is what we see. The big one is the voltage derate, and that's typically 60%.
Okay, great. Thank you, Misha. That's all the questions we have time for today. If we did not get to your question, please feel free to reach out to Misha at quanticevans.com and we'll be happy to follow up with you. So with that, thank you everybody for joining and thank you, Misha, for this excellent presentation.